Good morning, everyone. Hope you had a good weekend. We are just getting into chapter 14. So we started it last day. And chapter 14 is about multivariable functions. So functions with multiple inputs and a single output. What we did last day was we looked at, for example, evaluating.
Excuse me, sir.
Oh, yes.
We can't.
Are you not able to see? Is my screen share not happening?
No, we can't hear you just now, but now we can.
Now you can? Everything's
Yes.
good? Everything's
Yeah.
good? Okay, perfect. Thanks for letting me know. All right, so I'll just reiterate what I said, which you probably didn't hear. So I said on Friday we introduced multivariable functions, and so these are functions with multiple inputs and a single output. And we looked at how to evaluate these functions at some given inputs. We also looked at what it means to graph these functions as well. So find the set of all points such that you've got the inputs as some collection of coordinates and then the output as an additional coordinate. Now today what we're going to do is we're going to get into a bit of the calculus, and this is limits and questions about continuity. This shouldn't take very long, so maybe the last few examples might take the duration of the rest of the class, but I'm not anticipating they will, which means we will likely get into 14.3 today as well, which is the derivative or partial derivatives. So let's have a look at this first example of this first problem. So we've got functions f of xy, and this should be a correction here. This is g of xy. So we've got these two functions, multivariable functions. And I should say this, there's a subtle point here, is that you'll sometimes hear me say multivariable functions. Multivariable means there's multiple inputs, as opposed to if I said multi-valued functions, that means there's multiple outputs. So what we looked at last week with our vector valued functions, so vector valued or multi-valued functions means there's multiple outputs. Multivariable functions means there's multiple inputs. And of course we could put those together. Multivariable, multi-valued functions means multiple inputs, multiple outputs, but we'll get to those at the end of the term. So there's just a subtle distinction in terms of language here. So here we've got two multivariable functions, and we are asked to complete the table. What is the limit as x goes to 0 of f of x, comma, mx? So let's have a look at that. And it's asking us for multiple values of m. So we're interested in the case when y is equal to mx. That's what it's telling us. We're plugging in mx for y. And so we're going to look at our function f of x mx, which is x goes in for x, and what we're plugging in for y is mx. And so this has our common x in all terms, so we can cancel them off, and I get a 1 over 1 plus m. So now I can work out what the value of the limit is as x goes to 0 of this function, because, oh, there's an x squared. Yes, thank you. Thank you. X squared. Sorry, so all of them cancel except for a single x up top. Thanks for catching that. So now I'm going to take the limit of this. Now this is a limit of a single variable. So now we can say what's going on as x goes to 0 of this function of a single variable. That's asking what's going on as x goes to 0. So what's the limit as x goes to 0 of x over 1 plus m? And that's equal to, because m is some fixed number, we're going to look at it in the table above for either m equals 1 or m equals 2 or m equals 3. But for any number we put in there for m, the limit as x goes to 0 is going to be 0. This is for any m. And so this is going to be 0, 0, and 0. So when m is 1, the function is x over 1 plus 1, or x over 2. When m is 2, the function was x over 3. So let's just jot that down just so you can see what it is we're doing. This is equal to x over 2. When m is 1, it's equal to x over 3 when m is 2, and it's equal to x over 4 when m is 3. And no matter which one of those functions I'm considering, they all have the same limit as x goes to 0, and that limit is 0. So that's that first row of the table. What about the function g? Y equals mx. G of x mx is x over x plus mx. And we're going to do the same thing. So in this case, when we cancel out the x from everything, we get a 1 over 1 plus m. And so now we're going to look at the limiting value of this function as x goes to 0. So again, we've eliminated the y variable in place of an x. In fact, we made it m times x. And now that becomes a function of a single variable. In this case, it's just a constant function, 1 over 1 plus m. So the value of its limit is 1 over 1 plus m for any m. I say for any m, but really we're meaning m not equal to -1, because then we'll have problems in the denominator. So for any m not equal to -1, not equal to -1. I probably should exclude that case. But what that means is that this is the value of our limit. So in the case was when m is 1, our value of our limit is a half. In the case when m is 2, the value of our limit is a third. And the case when m is 3, the value of our limit is a quarter. So f and g, although they look very similar to each other, they're both x, in one case it's raised to the power of 2, and the other one is raised to the power of 1, over the sum of x plus y. They behave very differently around the origin, around 0, 0. Now, if you think about what we've done here with f, with this plugging in y equals mx, we can think of this in terms of our input plane. So where are our values x and y coming from that we're plugging into our functions f and g? Well, what I'm doing is I'm taking a line, y equals mx, and I'm watching what happens as I go along that line to the origin. So as I travel along that line to the origin, as x goes to 0, I'm traveling along this line because I've taken y equal to m times x. Then this tells me that for the function f, no matter which direction I approach 0 from along whatever line I take, my function value f is always going to 0. Whereas for the function g, this tells me that it depends on the direction I'm coming to the origin at. If I come along the line y equals 1x or y equals x, then my limiting value of my function g is a half. And similarly for the other ones. They're different values. So they depend on how you approach 0, 0. So in terms of limits, we have to take that into consideration. We have to take the direction in which we approach the xy value we're interested in. We have to take into account we can come at it from different directions and different things can happen. So that's what we have to build into our definition of our limit. And so here's our definition of the limit for multivariable functions. It says let f be a function of two variables, and the domain includes arbitrarily or points arbitrarily close to a, b. So AB is the point that we're going to take the limit as xy go to that point. So we say that the limit of f of xy as xy approaches AB is L, provided, and I'm just going to paraphrase this here, provided we can get our function values as close to L as we like by taking our inputs as close to AB as we like. So this is the whole plain language limit we had from Calculus 1, that the function values can get sufficiently close to L provided we take the input sufficiently close to A. In this case, we just can ramp this up to the next dimension. The limiting value of f is L, provided we can get sufficiently close to L as we like with our outputs by taking our inputs sufficiently close to the point AB. Now, sufficiently close is a very hand-wavy term, so we need to tighten this up a little bit, make it a little bit more rigorous, and that's where this epsilon and this delta come in. And so what this statement actually says, tries to tighten up the idea of what a limit is, and it really is capturing this idea. I've got this point AB in my domain, and I'm letting points get closer, and xy values get closer and closer and closer to that AB value, and I want to know what's happening to my function value at that point. So sort of go up to my function here, and my function maybe looks like something like this. So it's going to be a surface, and there's my point that I'm thinking of as being the limiting value L. So that's what I'm thinking L is going to be. And what this says is, yes, that is the limiting value, provided the following happens. Provided I can take a small interval around L, that's where the epsilon comes in. So that distance between the edge of that interval and L is epsilon. So this top point here is L plus epsilon, and the bottom point of this interval is L minus epsilon. So I give us a target, and I want to know, can I always land in that target by taking my inputs sufficiently close to AB? So that's a question of, can I take a circle around AB of some radius, which we'll call delta? So can I take this delta, I'll zoom in a little bit, can I take this delta radius such that every point in this circle around AB of radius delta, when I see where it goes up in my diagram, what I get are points that live sufficiently close to L. In other words, in this epsilon sort of envelope around L. And if I shrink epsilon, can I still find a circle around delta, or sorry, circle around AB of radius delta, such that all the points in that circle land within epsilon of L when I take their function value? That's what's summarized here in the definition. So it's saying that if for every epsilon that I choose, no matter how small it is, as long as it's bigger than 0, that gives me the target along the z-axis around the L that I'm trying to show as the limit. I can find a delta that is a radius of a circle that is small enough around AB so that whenever xy is a point in that circle, that's what this thing here says, is that xy is in the circle, because its distance from AB is less than delta, then the function value is within epsilon of that limiting value I'm trying to show, L. So if xy is close enough to AB, then the function value is close to L. That's what this is saying. If that's the case for every epsilon, I can always find a delta, then the limiting value is L. Okay, so that's the formal definition. We will probably use it just once. I'll show you how to use it just once, but we'll see that from this, we have limiting law or limit laws that we can use, squeeze theorem and the like, and those will be the way we compute limits. But this is the definition of the limit. We'll see how, much like in Calculus 1, we had a definition of a limit. You may or may not have seen the epsilon delta definition, but it was there. But we learned how to compute limits using limit laws. Okay, so let's have a look at an example. Let's evaluate or show this limit does not exist. So we have to decide whether it exists or not, and then show what the value is if it does exist. And in this case, what we're going to do is we're just going to get our hands a little bit dirty to start with, get a feel for what's going on. I'm just going to say, well, why don't we, so we're interested in going 0, 0. So maybe I'll draw a little picture first. We're interested being in the XY plane. We're interested in points that are getting closer and closer to 0. And I have to come at it from every direction. If I want to show that the limit exists, I have to show that it's independent of the direction I come at it from. But why don't we just get a feel? Let's just come at it from one direction and see what happens. So maybe I'll come at it from this direction here, along the x-axis. So along x-axis. Along the x-axis, y is equal to 0. So what we'll do is we'll look at the function value. Let's just name this thing f of xy. So we're going to look at what happens as I come at it along the x-axis. So the y value is 0. And, oops, I need to make that second y value 0 as well. So maybe I'll put the 0 in there just so you can see that I've plugged 0 in. I get an x squared over a root x squared, or in other words, an x squared over the square root of x squared is the absolute value of x. And so x squared over the absolute value of x is the absolute value of x. So that's what our function is doing for values along the x-axis. And in this case, I can say, oh, well, the limit as x goes to 0 of f of x comma 0 is just the limiting value of absolute value of x, which is 0. So this tells me that if the limit exists, it's going to be 0. I don't know that it exists, though, because I don't know if I come along a different axis or a different line, my function value is going to be different, like the example we had up here. If I come at G, or if I come along G along different directions, so if I come along different lines, y equals mx for various values of m, then I get different values of the limit, in which case we would say the limit doesn't exist in that case. So just knowing that if I go along one direction, the value of the function is tending towards 0, it doesn't tell me that the limit is 0. So we want to show then that the limit is actually 0. And this is the one case, this is the one time I'll do the epsilon delta argument, just so you can see how it works. But in the next examples, we'll be using other techniques for showing that the limit exists. So let's do our epsilon delta definition. So we start with, I'll do it in a different color. Given epsilon bigger than 0, we need to choose delta equal to something. And we'll fill that in a second. So given a target along the z-axis around 0, in this case we're trying to show the limit is 0. So given the target of epsilon around 0, I need to find a radius of a circle for which anything that starts in the radius of that circle always lands within epsilon of 0 in the output. So let's say then for So we basically copy out a lot of the definition because that's what we need to show. Then for this xy in the domain, such that it's within delta of the point 0, 0, a, b in this case is 0, 0. So that statement, this statement right here about being in the circle of radius delta about AB, that statement A and B are both 0 because we're approaching the origin. So that reduces down to this square root of x squared plus y squared. So given that that is less than delta, we have, now we want to show our function value is within epsilon of the limiting value. The limiting value we're trying to show is 0, so I need to look at how big f of xy is, or how far away f of xy is from 0, given that my input xy is within a delta radius circle of the origin. So this becomes then our function value over square root of x squared plus y squared. And now I need to figure out how to use the fact that the square root of x squared plus y squared is smaller than delta to try to show that this thing is smaller than epsilon. So one way to do that is to realize that x squared plus y squared square root is the same thing as, there's a square there. I can write that denominator as a square root of x squared plus y squared over x squared plus y squared. So notice I've just split up that square root in the denominator into a fraction, which is equal to the 1 over the square root. It's the square root on top and just the quantity on the bottom. So I've just introduced an extra term in a bit of a fancy way. I haven't changed the value of anything. I've just introduced it in a way such that when I split this up now, x squared plus y squared, square root of x squared plus y squared. When I split this up, I see that square root of x squared plus y squared in there. That's what I want because I know that's less than delta, because xy is within the delta radius circle of the origin. But I also have it set up so that I can see that this thing can't be any bigger than 1 because it's x squared minus y squared over x squared plus y squared. So the denominator is bigger than the numerator. And since the denominator is bigger than the numerator, this has to be at most 1. So that tells me that this is at most the square root of x squared plus y squared. And I want that to be less than epsilon, but that's equal to, or that, sorry, that's strictly less than delta. So that's strictly less than delta by our assumption that we are in this delta radius circle about the origin. And so if that's strictly less than delta, then as long as I choose delta to be the same as epsilon, so notice what I've done now, I've filled in this spot. How am I going to choose my delta? I've got my target for my epsilon interval around the limiting value 0. I'm going to choose the radius of my circle to be the same as that targeting value, that epsilon around the output. I'm going to choose my circle to be that same radius. And so this becomes epsilon, which tells me that my function value is within epsilon. There's a strictly less than sign here, so it's within epsilon of 0 whenever my input is within delta from 0, 0. So this completes that epsilon delta proof. So therefore, the limit as xy goes to 0, 0 of f of xy is equal to 0. So that's our delta epsilon proof, or epsilon delta proof. As I said, I was just going to do one example just so you can see, get an exposure to an epsilon delta argument. You're not going to be asked to do an epsilon delta argument on an exam. This is not something I'm going to ask you to do. But I will ask you to do the further kinds of arguments we're going to do, the using the limit laws, etc. So let's just see another example. Today, I just hope to get through a number of examples of limiting values and to try to impress upon you what these ideas are and how direction matters as you come to the origin. So we're going to look at this next example. What's the limit as xy goes to 2 comma negative 2 of this function? So we can do the same kinds of things we did in Calculus 1. I mean, if you think about how you worked out limits in Calculus 1, probably the first thing you did was just, let's plug it in and see what happens. If I get a 0 over 0 type limit, then I know there's more work to do. Maybe L'Hopital's rule, if you were sufficiently advanced far enough along in the course, you knew that, you could do that. Or if it was type 0 over 0 earlier on in the course, then you do some algebra, simplification, try to factor some stuff out. You do basically algebra to evaluate limits. And we can do the same kinds of ideas here. If I look at this one and I say, what's going on as xy goes to 2 negative 2? Well, I can just pop it in and see what happens. As xy goes to 2 comma negative 2, the numerator is going to 4 minus 4, or 4 plus 4, or 8. Whereas the denominator, what's the denominator going to? As xy goes to 2 comma negative 2, yeah, you got the numerator goes to 8, and then, yeah, the denominator is going to 0. So does the limit exist? Yeah, no, the limit doesn't exist. So it's blowing up. It's either going to positive or negative infinity, but that's not a number. So the limiting value being plus or minus infinity is not telling us the limit exists. It's telling us exactly how the limit does not exist. So I just want to reiterate the fact that for those of you who are looking at this going, oh, then the limit should be infinity or maybe negative infinity. That's a description of how it doesn't exist. So this, we would get that the limit does not exist. And so we could write the limit as xy goes to 2 comma negative 2 of 4 minus xy over 4 plus xy does not exist. That's sort of a common way to write. And of course, the reason is because the ratio is not approaching a particular number. We've got the top's going to 8, the bottom's getting really, really small. So the ratio's getting really, really big in magnitude and not going to a particular number. So the limit doesn't exist. So those kinds of arguments are sufficient. We can do these arguments here as well, just to borrow from the fact that we have a lot of knowledge from Calculus 1 and we can use it here. So with that epsilon delta definition, where it is important is to prove the limit laws. So we can prove all of these limit laws using the epsilon delta definition. We won't do that. We will take these limit laws as fact, or as laws in the case here. I'm not saying that these are limit theorems. I'm just going to say they're laws. They're things we're going to use, and I'm not going to prove them. They're just facts we're going to accept. So the limit of a sum, the limit of f plus g, is the sum of the limits. In this case, if the limit of f was L and the limit of g was m, then the limit of the sum is L plus m. The limit of a product is the product of the limits. The limit of a quotient is the quotient of the limits, provided the bottom is not 0. And then we also have the squeeze theorem holds for multivariable functions as well. And the squeeze theorem turns out to be of a lot of use for us here. The way we use the squeeze theorem here is we try to squeeze the function which has 2 variables in between 2 functions which are single variable functions. And if we can do that, then we can use our calculus, our limits of single variable functions. So let's see an example of such an argument. So let's find this limit if it exists. 2x y squared over x squared plus y squared. So the first thing I'm going to do again is I'm going to call this function f of xy just so I can use the name later on. So let's call it f of xy. And now let's get a feel for how big it is. How big is f of xy? Well, f of xy is 2xy squared over x squared plus y squared. And I'm just going to draw your attention to this part here. The y squared over x squared plus y squared. How big is that? Oh, sorry, I just peeked at the comments. 2, -2. Yeah, I got 2, -2. It looks like. Okay, sorry, I thought I might have miswrote 2, -2 just based on the peeking at the comment, but maybe you were talking about something else. So how big is this thing? Y squared over x squared plus y squared. Yeah, it's at most 1. This thing is at most 1. Because, again, the same idea we had before, the denominator, x squared plus y squared, is bigger than y squared. So that forces that ratio to be at most 1, which is nice because that's at most 2 times x in magnitude. And so I have also that this is at least 0. So this tells me that my function f of xy is trapped between 0 and 2x in magnitude. So 2x and 0. So as x goes to 0, 0, as x goes to 0, as xy goes to 0, 0, what we have is that f of xy, which is trapped between 0 and 2x, well, that's going to 0, and that already is 0. So my function is trapped between two quantities, each which are going to 0 or already are at 0. So my function values must be getting close to 0 as well. They're being squeezed closer and closer to 0. So therefore, f of xy goes to 0. And so that means our limiting value, which I can fill it in now up top, our limiting value is 0. So I'll write down our conclusion as well down here just to complete the argument. So the limiting value is equal to 0. It was trapped between two functions, which were going to 0. So it itself had to go to 0. So these are the kinds of arguments that we can use. Squeeze theorem turns out to be quite a powerful one to use here because we can squeeze it between, perhaps we can squeeze the function between two single variable functions and then use our results from calculus 1 on those single variable functions. Okay, so
Jamie?
yes,
Jamie?
yeah.
I have a question.
Sure.
How come sometimes when we use the squeeze theorem versus using L'Hopital's rule, we tend to get different limits?
So L'Hopital's, you tend to get different functions that you're working out the limit of, or different limits in general, like different values?
Different values for the limit.
Okay, we shouldn't get different values. If we get different values, then that's an indication that something's gone wrong. Maybe the limit doesn't exist. But the value you get from L'Hopital's rule should be the value of the limit, provided that all the hypotheses were satisfied for L'Hopital's rule. The numerator is going to 0, the denominator is going to 0, and therefore you can compute the limit in terms of the limits of the derivatives of the top and the bottom. Or in this case, if it's a squeeze theorem, that the two functions that you're bounding your function you're interested in finding the limit of, the two limits of these extremity functions goes to the same place. And so the one in between must go to that same place as well. So you should get exactly the same values. If you get different values, something's gone wrong.
Okay, I'll have to look at that again then.
Okay, yeah, and then you can always feel free to send me the example and we can talk through it.
Okay.
Okay, so then now that we have the notion of a limit, we can talk about continuity. Continuity of a function at a point. Well, a function is continuous at a point if the value of the limit is the same as the value of the function itself. So remember this continuity, it's the same as it was for calculus 1, but it says that the limit exists, the function value exists, and the two of them are equal to each other. The limiting value is the same as the function value. That's what it means to be continuous. So we can look at an example. Find the value of k so that this function is continuous on all real numbers. So really the key here is that, let's just make one observation first, is we want to show that it's continuous on all of R2. So I need to show that for any a, b, the limiting value is the function value. So I'm just going to make the note that for a, b not equal to 0, 0, the limit as xy goes to ab of e to the negative 1 over x squared plus y squared. As you might imagine, there's no issues with just plugging ab in for xy. We're not dividing by 0, assuming ab is not 0, 0. We can take the exponential of it. There's no problems. So much like in calculus 1, there's no issues with just popping the value in. In other words, there's no issues with just realizing that the limit is just the value of the function in this case. So that means that f of xy is continuous at any ab not equal to 0, 0. Okay, so that's the first thing. Now, the one that we're really interested in is what about 0, 0? Is it continuous there? So to be continuous there, we need that the value of the limit of the function is equal to the value of the function. And these are often the kinds of questions we get where they're piecewise. And we've got that the function is defined in one way on part of the domain, and it's defined in another way on another part of the domain. And we just want to make sure that these things match up, that these definitions match up. So how should I define the function at 0, 0 to sort of fill in a hole if there was a hole left by the exponential part of it? Because we can't divide by 0. So in the exponential part, it doesn't make sense to plug in 0, 0. So I'm going to have to explicitly say, well, this is what you do in that case. When your input is 0, 0, define the function value to be this k value. Okay, well, what's the most appropriate value to make k equal to so that things are continuous? Well, that's where we want to decide what is the limiting value of our function as we go to 0, 0. What is the limiting value? Because whatever this value is, if it exists, that would be an appropriate choice for k. So let's see, what's our limiting value? The limit as xy goes to 0, 0 of e to the negative 1 over x squared plus y squared. And again, don't forget that we've done a few examples now, epsilon delta argument, which you won't need to probably do on any further examples unless there's one on the assignment which is asking you to sort of do it. But in general, when we're looking at a problem like this, we don't need to worry about the epsilon delta argument. Let's just think about plugging values in first, and if not, maybe a squeeze theorem as your first reaction. You should be like, okay, what happens if I just plug the value in? So what do I get? If I plug in 0, 0 for x and y, what is that expression going to go to? So we get that This bottom is going to 0. So what's the ratio? Some -1 over something that's really small. Yeah, I see what the final answer is there. Thanks. Yeah. So exactly, the whole thing is going to 0, but let's see how, and since I've already started the discussion. So the bottom's going to 0. So -1 over something that's really small is going to something that's really big in the negative. And then we're taking e to the power of something really big. E to the power of something really big, or negative, a really big negative, becomes 0. So we're just using our ideas from Calculus 1 as we had before. E to basically e to negative infinity, we're thinking of, okay, that's going to 0. So that means then for f to be continuous at 0, 0, we need the limiting value as xy goes to 0, 0 of f of xy to be equal to the function value. The limiting value we found to be 0. The function value is k. So that tells us we need k to be 0 in order for it to be continuous. So that means if we're interested in defining this function and we wanted to make sure it's defined at 0 as well, that's what we should do. We should put a 0 in there for its function value at 0, 0, and then it's continuous. Okay, so that was very similar to the kinds of questions we did in Calculus 1. Redefine a function at a single point and do it in such a way that it's continuous, or piece two functions together and do it in such a way that it's continuous. And then we just had to find the limiting value of the function and the function value and make sure they were the same. Okay, so for these next couple of examples, we're just going to test for continuity at the origin. What's the value of the limit? What's the value of the function? Is it continuous there? Let's have a look at this first one. So what's going on? I've got an xy over x squared plus y squared, and I want to know what's happening as xy gets closer and closer to 0. So I'm just going to say, let's try our hand at a few different directions. So suppose we come along the x-axis. That means we're coming along y equals 0. And so what do we get in this case? F of x0 is 0 over x squared, or 0. So that's the function value at any point along the x-axis. So as xy goes to 0, 0, maybe I'll remove the y and I'll just continue talking about along the x-axis. So as x0 goes to 0, 0, f of x0 goes to 0. So as I go along the x-axis, my function value is approaching 0. In fact, my function value is 0, but that doesn't make it any less truthful that the function values are going to 0. They're actually already there. Okay, so along the x-axis, our function's going to 0. Maybe 0 is the limit. Okay, so maybe 0 is the limit. Maybe we should try to think about proving 0 is the limit. Or maybe not. Maybe 0 isn't the limit. And if I come along a different direction, I'm going to get a different answer. Let's try along the line y equals x. So along the line y equals x, I'm looking at my function value is going to be f x comma x. Or in other words, x squared over x squared plus x squared, which is x squared over 2x squared, or 1/2. Ah, that tells me that if I come along a direction that's not on the x-axis, but a different direction along the y equals x direction, my function value is a half. So as xx goes to 0, 0, f of xx goes to a half. So it depends on which direction I come at the origin from. If I come along the x-axis, my function values go to 0. But if I come along this other line, y equals x, my function value goes to a half. Those are two different values, and so the limit can't exist because it's dependent on direction. So therefore, limit does not exist. Okay, so you might be thinking, well, what does this even look like? You know, how can such a thing happen? So I've put some examples in the lecture notes schedule. So we're on limits and continuity 14.2, and I've got this demo, exercise 8a. If you click it, it takes us to, well, maybe I should click it to get it to load. Let's see. Here it's loading. So you can see our function there, xy, x squared plus y squared. So there is our function. It's got this kind of crinkle in it. You may look at it without even that yellow thing, whatever that yellow line is in the dot. Don't even worry about that for a moment. If you look at this thing with a crinkle in it, you might say, oh, that doesn't look to be continuous. That's got some weird sort of stuff happening there. And that's really what we're trying to exploit here, is notice that as I come along, I can't even get to the x-axis, but I'll go along the y-axis because it's, let's see, along the y-axis. So there we are. So as I come along the y-axis, my function value is 0. And so as my point gets closer and closer to the origin, my function value gets closer and closer to 0. But this is where interesting things happen. If I come at it from a different direction, so there's our very close to y equals, let me get it to 1 there. That's our y equals x direction. So I'm coming along y equals x. And as I come along y equals x with x getting closer and closer to 0, my function value, if we look, my function value gets closer and closer to a half. In fact, it's staying at a half. And that's what we've picked up. Along the direction y equals x, my function value is a half. If I change the direction, if I come along various different lines, I can get various different heights. So this is what we're capturing here. Yeah, so that's a good comment. Most of the times, yeah, you're going to be looking at different directions, coming at it from different directions to see if you can immediately spot two directions that give different values. So let's have a look at the next one. I'll give you another bit of a hint as to what to look for as well. Maybe I'll say it this way, first of all. The top in this case for our rational functions, we had an xy and the bottom was an x squared plus y squared. The top is, if you think about terms of like a degree, maybe you can think of the top as being like a degree 2. There's two of the variables being multiplied together, and the bottom's also degree 2. You got a square and a square, and it was really that was causing things to cancel out when I come at it from different directions along a line. Y equals x. I was able to join things up and have an x squared up top and an x squared on the bottom, which canceled out, and that helped a lot. So in some sense, powers have something to do with this, what to look for. So in this case, we've got an x and a y squared. So we've got, you know, like a degree 3 kind of thing going on up top and only a degree 2 on the bottom. So that means that as we go to 0, 0, we sometimes, in some sense, got something that's of higher power on top than the bottom. And that thing that's higher power up top is going to 0. So is the thing that's like a degree 2 thing on the bottom. And so I expect the fact that I've got a higher power up top of a 0 to maybe go to 0 faster than the bottom. And so maybe I expect this thing to go to 0. These are the kinds of things you can start to play around with as you do examples. To make it precise, though, we've got to go with the following. So f of xy is equal to this expression here. And I could say, well, like I said before, I kind of expect the top to be going to 0 faster than the bottom. I can make that rigorous. I'll throw absolute value signs on the bunch. And then I'll notice that, hey, wait a minute, this thing, that's less than 1. So this is less than or equal to absolute value of x, and it's bigger than or equal to 0. So my function is trapped between 0 and x. And so by the squeeze theorem, the limit as xy goes to 0, 0 of f of xy is equal to 0, because the two things I've trapped it between are both going to 0. So that's going to 0. Let's have a look at one more. I should be, oh, we're at 9:20. We'll be able to wrap this one up really quickly as well. Actually, I encourage you also to play around with this 8b. So I've got the demo there for 8b as well. And you can try to look at what happens as you come along different directions. And you can see that we're always, no matter which direction I come along, my function value is always going to 0. So you can have a look at that as well. All right, the last, the C here, I just want to do it to wrap this sort of up, because again, this is something where you've got on the top, it's like a square. On the bottom, it's like a square of the sum of squares. So that's an indication that this thing is probably going to behave differently depending on which line you approach along. Notice this is a function of 3 variables now. So now we've got all different directions to approach the origin in 3 dimensions, and we're looking at the output value, which is in the 4th dimension. And we want to show that that's not continuous. And so in this case, we can say, you know, what's happening along the line. Now we know how to define lines in 3 dimensions. So I will say along the line x, y, z is equal to, let's say, x, mx, and x. So if you're a little bothered by that, what I'm really saying is we're looking at r of t is equal to t times 1 m1. So we're coming along this line for some arbitrary m value, which I'm allowed to change. I could take m to be 0, 1, 2, 3. Those are just different lines. So, but instead of using the t variable, I'm using the x variable as my parameter. And so then when I pop this in, x, y, z, which is f of x, mx, and x, I get mx squared over x squared plus m squared x squared plus x squared. All the x squareds cancel. This is where I'm using the fact that the top was kind of a degree 2 thing, the bottoms were degree 2, so if I made a linear substitution for the variables in terms of each other, I can get all this cancellation happening. So this becomes an m over 2 plus m squared. And that means this depends on direction. The value of the function depends on which direction you approach the origin from, and therefore the limit does not exist. All right, so that's it for the lecture. I'm just going to stop the recording.